Yeah, hello. How are you? Good evening.
Good evening.
So it's night time there, right, at Malaysia?
It is now 10 p.m.
Oh my God. So,
But
okay.
it's okay. No worries.
Yeah. So, participants, it's my pleasure to introduce Hrisab Bakul who is a robotics and AI scientist at TCS Research India. Currently, he is on leave to pursue his PhD at Monash University, Melbourne, Australia. He's also working with Monash University, Malaysia. He has received PhD fellowships from universities across 5 different countries, including USA, UK, Ireland, Australia, and Malaysia. He completed his master's from Jadavpur University, Kolkata in 2018 with first class second rank. He has filed 22 US, Europe, and Indian patents, out of which 14 have been granted so far. He has been invited to many premier Indian and foreign institutes for delivering talks such as IIT, IIM, NIT, New York University, etc. He has received numerous prestigious grants and awards from various organizations. His team at TCS Research received the Best Research Team Award for the year 2020. His work has also been included in a course at the University of Florida, USA. He's also published several papers in top-tier venues in the field of computer vision. With this short introduction, now I'd like to request Mr. Rishabh Barwa to kindly start the session. Over to you.
Thank you, Professor Deepak, for this nice introduction. And also thanks to you and the entire organizing committee of this workshop for having me as a speaker.
Yeah.
So without much delay, let me start sharing my screen. Is my screen visible?
No.
Okay, just give me 1 second. Now I think it is visible.
Yeah, it is visible.
Okay, thank you so much. So so what I am going to talk today is about a very important problem in computer vision, which is reconstruction of images from one particular domain to another particular domain. So specifically, in this case, we are talking about low dynamic range LDR images to high dynamic range HDR images. And why this problem is important and what are the application areas that we are going to explore in the coming slides, and some of the recent works that we have done in this domain. So to set the tone of the this area. So low dynamic range images are those images which actually have a very small range of intensity values. Generally, there are normal images that we have that are been clicked by normal cameras, not the high-end cameras, are in low dynamic range. That is represented by 2 to the power 8, number of intensity levels, that is 256. So in those cases, when we have a very highly lit environment or environment with many shaded areas or dark areas, then it is not clearly seen what are the things and objects present in those areas, whether it is highly lit or it is low lit. And hence, it is important to devise methods which can convert this kind of images and videos to high dynamic range images and videos. Now, these high dynamic range videos or images have a much higher or a much wider intensity levels, more than 2 to the power 8. So it can be 2 to the power 10, 2 to the power 15, 2 to the power 20. So it has a very large gamut of intensity levels. So when we have an image in high dynamic range, HDR, then we can clearly see the foreground, background, and all the things in the image, whether it is highly lit or it is low lit. So here in this image, in the first slide, you can see the upper row consists of images that are in low dynamic range format, and the lower row consists of images which are converted to high dynamic range. Okay, so you can see the clarity of these images compared to the low dynamic range counterparts. So with this, I would like to go into the presentation. So why it is important? So problem statement. So what the problem currently faced by the vision community or researchers in this domain. Okay, so HDR content, as I already said, from low dynamic range images and videos lacks perceptual quality. So even if there are methods that converts LDR to HDR, but there are issues with perceptual quality, the luminance levels, the brightness levels, contrast, saturation, all these things are not reconstructed in a proper manner if you convert from LDR to HDR. And also, as per the human vision system, so the ease or the way we see real life scenes through our eyes, this thing is replicated in the human vision system. And we need to create the HDRs in such a way that it looks like real scenes and not just a generated or a reconstructed scene. So this from the perspective of human vision system, the generation of HDR images are not, or the images that are generated in HDR format are not very visually pleasing in nature. So these are the problems that are being faced by the current community, research community in this domain. Also, to train deep learning models, we need huge amount of data, as we all know, right? So it is important that we have good, data of LDR HDR pairs to train huge models consisting of transformers or diffusion or etc. Similar kind of models that we use nowadays. So the importance of HDR imaging see in many application area. For example, segmentation in robotics and AI, self-driving cars, depth estimation, illumination estimation, SLAM for robotics, that is simultaneous localization and mapping for robotics to generate the maps of the environments where the robots work. And the most recent ones are related to immersive visualization, like virtual reality, augmented reality, and so on. So as I already said, so there is a lack of data, as well as there is a sufficient gap in the models to develop or to reconstruct the HDR images from the low dynamic range counterparts in a visually pleasing way. So that is where we come in and we try to mitigate this gap. Okay, so now here, before going to the recent works that have been done and how these works are solving some of the existing problems in this domain, so I'd like to set the tone about HDR imaging and also deep learning in this domain. So in the left-hand side image, you can see this is a typical camera pipeline where a camera clicks images and how the images are stored in HDR format and later on tone map to low dynamic range, counterparts. So HDR images takes a lot of, space to store. So normally the cameras, whenever you click an image using your camera, it normally first takes the uses the sensor irradiance from the lens, then the exposure time, and then from these it gets the HDR image. And then when it gets the HDR image, it performs dynamic range clipping. That means it clips the intensity values that does not fall in the 2 to the power 8 intensity levels, that is 256 intensity levels. Then it does quantization of these intensity levels. And finally, nonlinear mapping is done from high intensity to low intensity level. And then we get the low dynamic range image. Now, our job is to approximate this process in the reverse way. That is, from LDR to HDR, we need to create a model which can translate LDR images to HDR images using a deep learning model. And this deep learning model will be trained on the parameters theta. And the main thing is that we need to set this parameters theta somehow by making it learn from huge amount of data. So that is the idea, overall idea of using deep learning in this domain. So the right-hand side image is a typical deep learning setup where we need to input LDR image at one end, and we need to get the generated HDR image in the other end. And we train this using LDR HDR pairs, right? So there will be some losses. With these losses, we'll actually find the or mitigate the difference between the generated HDR image and the ground truth HDR image. And then finally, after that, we need to do the quality assessment of the generated images. So we have some referenced quality metrics or matrices, which can then take the generated image and the ground truth image and find the difference between these two and give the quantitative evaluation. Again, we can use this referenced quality metric to train another model which can actually predict the quality score of the generated HDR images. So that is again another model. In the site, you can see a pink color model. So this model is again trained on the basis of ground truth quality scores and the ground truth HDR images. And then when you give a new HDR image, new generated HDR image, it will be able to predict the quality score, having trained on huge amount of quality score and HDR pairs. Okay. So this is just a very generic overview of what we want to do in this domain. So now, for today's talk, I am included these 4 different things, and we'll be talking about these 4 different things one by one. So first one is the impact of histograms in HDR content creation, specifically images in this case, because we are currently working in the image domain. And then we will talk about the data gap in the training process and how we can mitigate this gap. Then we can talk about how, if there's not much data available, or if the data is not paired, that means we do not have LDR HDR pairs, rather we have a set of LDRs and a set of HDRs, and we just can use this set of LDRs and HDRs without having one-to-one pairing. Then how to do that in a deep learning model. So working on unpaired data or self-supervision. And finally, how physics can come into rescue in this case. How you can create realistic high dynamic range images from low dynamic range images using physics-based modeling. So now first we'll go into the first number 1, the impact of histograms in HDR content creation. So here, this is one work that we did recently, where we tried to study if we can use histogram equalization to enhance the quality of HDR generation. So at this point, I would like to say that histogram equalization is a technique by which we actually enhance images, right? We try to enhance the images to a better viewing experience. So there are other such kind of techniques like gamma correction or Retinex-based correction, which can be used for enhancing images. So if there is a very dark image or if there is a very bright image, then we can convert or we can lower the darkness or lower the brightness of these images using histogram equalization. So we designed a model where we actually extracted features from the ground truth LDR image, and we converted this LDR image to a HDR image using this model. So here, the main part is that we have taken histogram equalized version of the LDR image and extracted features from this image as well. Then we concatenate these features, we pass it through a very simple self-attention module, and then we decode the image and we get the HDR. So in this case, we have found that histogram equalization significantly improves the clarity of generated images. So in the lower part, you can see how our method's image, you can see that there is something written in the board, although not in English, it is in Chinese. So the clarity of this board compared to the LDR image and the other state-of-the-art models output. So this proves that how histogram equalization can impact positively in the image translation task. So this may be helpful in other image processing or image enhancement tasks rather than only using it in HDR domain. So in this case, we have used multiple loss functions. I will not discuss all the loss functions in detail because these are already existing losses. So I would like only to talk about loss number 8. That is a loss inspired from a structural similarity loss calculated between two images in image processing domain. So we have used this structural similarity metric to design this new loss function. So we call it SSIM. And then another loss is the equation number 7, that is a modified PSNR. So we all know that PSNR measures the noise in the generated images compared to a ground truth image. So this is a modified version of PSNR where we slightly modify the PSNR equation to get a Weber equation. We call it Weber equation. So loss W is the representation of this Weber loss. And finally, the equation number 12, where we actually try to minimize the color difference between the generated image and the ground truth image. And we use it in this model for training. So these 3 losses are the novel losses that we have used in this method. Other losses are already present in literature. And we have found, or we can see good results using these losses. So in the left-hand side, you can see some of the images which we actually converted to histogram equalized versions. And you can see the difference between the histograms in green and orange. The green is the original image and orange is the equalized image using histogram equalization. So you can see that how histogram equalization actually tries to level the intensity values across the 2 to the power 8 intensity bins. And in case of the green ones, you can see how the intensity levels are not evenly distributed across the intensity bins. That is 2 to the power 8, that is 256. In the right-hand side, you can see some of the results from our methods output compared to other state-of-the-art methods. So the clarity that you can see in our images actually cannot be seen in other state-of-the-art methods compared to the ground truth HDR. That is the last column, HDR GT. So yeah, and these are some of the quantitative results in terms of 3 matrices we use: PSNR, peak signal to noise ratio, SSIM, structural similarity metric, and HDR VDP2. So this HDR VDP2 is a metric that actually is used for comparing, specifically comparing HDR images. So this is not for LDR images. So PSNR and SSIM can be used both for LDR and HDRs, but VDP can only be used for HDR images since it deals with more intensity levels compared to LDR images. So HDR VDP2 actually takes into account all the intensity levels present in an HDR image. That's why we get a better understanding of the generated image compared to the ground truth image using this metric. So a new version of this metric has also come up recently, which we call VDP3. Okay. So yeah, so this is the first one that we talked about, where we talked about histogram and the use of histogram in HDR generation. The second one is an interesting one where we actually, work on the data domain itself. So most of us might have played, different kinds of games at some point in our life. So we got inspired by video games, and we thought that why not use video games to generate data for this particular task. So we chose GTA HDR. Okay, so GTA game, all of us, we might have heard about this game. This is a very popular game, and many people still pay this game. So one good feature of GTA is that we have both the LDR and HDR mode to run this game. So we leverage this particular power of GTA, and we extracted images from the game playing data in both LDR and HDR format, and we created a LDR HDR paired data set out of this particular game. And this is the overall pipeline that we used, or that we designed to extract game playing data from GTA 5 game. So we use some off-the-shelf plugins like Script Hook, and then we extracted game playing sequences of 15 and 20 hours. Then we did data sampling and selected frames across these game playing sequences. And also we tried to see if there is sufficient difference between two frames while extracting the frames from this game playing sequences. Then we extracted 54,000 and 72,000 pairs from these two different sequences. We calculated frame similarity and discarded frames which are similar to a particular threshold. Then we did some manual cleaning. Then we created a 40,000 pairs of LDR HDR in this data set. And then we also created some distortions in the LDR as well as HDR by creating different contrast levels and exposure levels out of this generated HDR images. Okay, so here in the left hand side you can see a table where there is a comparison between our dataset and other existing datasets in this domain. So you can see most of the datasets are either small in size or the resolution is very less, and also they do not contain in the while scenes and different kinds of distortions in the HDR, and there is lesser scene and image diversity in these images of these datasets. But in our case, we have collected a huge amount of HDR LDR pairs, 40,000. Then the resolution is also acceptable, and we have in the while scenes, we have distorted HDR scenes, we have scene diversity, and we have image diversity. In the right hand side, you can see what kind of scenes we have included in our dataset. So there are city scenes, there are desert scenes, there are indoor scenes, outdoor scenes, beach scenes, wildlife scenes, forest, mountains, sea, then different weather conditions, foggy, rainy, snowy, sunny, cloudy, then different objects. So house, indoor, waterfall, building, shadow, boat, humans, vehicles. So everything is included. Even time of the day, morning, midday, evening, night. And in the lower image, you can see we also created different contrast levels, different exposure levels, and combination of different contrast and exposure levels in our dataset, so that the dataset gets full scene and image diversity, and it will help the deep learning models trained on this dataset to better generalize the problem. So these are some of the results we actually got by using GTA HDR dataset and other datasets. So here R means other real datasets, S means synthetic datasets, and the first subtable consists of results from only some real datasets already present. Second subtable consists of results from a combination of real and synthetic datasets. Third subtable is our datasets contribution, and fourth subtable is the contribution of real, synthetic plus our dataset. So you can see that the third subtable have better results compared to the first and second. And finally, the fourth subtable is the best among all the other results in terms of PSNR, SSIM, and Q-score. So the higher, the better. So this proves that our dataset is positively contributing to the domain gap present in the existing data. And also, we have benchmarked it in multiple state-of-the-art methods. You can see in the method column. So, and these methods consist of different models, like some are using CNN, some are using transformers, some are using diffusions, and so on and so forth. So it is clear from this table that any kind of model, be it CNN-based or diffusion-based or generative models, any other generative models that we have, so our dataset is significantly improving the result compared to other datasets. So here is a two-dimensional projection of features extracted from our dataset and other datasets. So there are we have selected three different datasets. So HDR, synthetic, and real in red color. Real datasets, a group of real datasets in yellow color, and another large dataset, CT-SIM, in blue color. And you can see the distribution of features across these datasets in the upper row, and in the lower row you can see our green color, that is the GTA HDR dataset that we have proposed, how the dataset is been able to cover a significant gap in the data domain itself. So in the first column, it is actually filling a gap in between the red color and the blue color, yellow color data. The second and third, you can see it is significantly overlapping some of the existing datasets, and also beyond that. In the fourth one, you can see it is significantly covering the top part of the distribution, the feature distribution. So from this, we can say that if we use our data in combination to the existing data sets, then there is a strong possibility of getting significantly better results compared to the other state-of-the-art methods which are trained on other data sets. Okay. So this is another representation where we check how only having one exposure level and multiple exposure level and contrast level change the landscape in the intensity level. So the green color is the histogram representation of the data in terms of single exposure. The middle one is for multiple exposure, and the third one is for both multiple exposure and multiple contrast level. So you can see that the multiple exposure and the contrast multiple contrast level data has a wide coverage of the intensity levels compared to the other two. So finally, we did some visual testing of our data set on one state-of-the-art method, and we saw that the histograms generated by the HDR images generated without using our data set is different from the one that is represented by the ground truth HDR image. But the HDR image that is generated by using our data set for training is quite similar to the ground truth HDR's histograms. You can see in some of the images. And also, the KL divergence between these two distribution is lesser in case of our datasets trained model compared to the model trained on other datasets. So this proves that our dataset is contributing positively to mitigate the difference between the generated image with the ground truth image. So yeah, and we also did some testing on downstream applications, how our datasets trained models are performing compared to models trained on other datasets. And we saw in 3 different applications that our datasets performance is better. So one is here, you can see the top image, the upper image. We tried to test it on human segmentation. So you can see our generated image human segmentation results are far better than overexposed and underexposed images. Similarly, in the lower part, the left-hand side image, you can see semantic segmentation of scene. A similar trend is seen. Our datasets trained model generates better images, which are been segmented in a more accurate way compared to overexposed and underexposed images. And the third image in the right-hand side, we also tried to use it in 3D human reconstruction from 2D images. And you can see our datasets generated images are actually, reporting better results compared to the overexposed and underexposed images. And the humans generated in 3D are far accurate in terms of their placement, in terms of their location in the image. So yeah, so these are the contribution that we have made in the data domain in terms of this problem of low dynamic range to high dynamic range image translation. So now coming to the third part. So now if we have data, so sometimes we also may have some applications where data is not readily available, or even if it is available, then the requirement actually makes us try some self-supervised methods or methods using unpaired data. So to this end, we also try to create a model which can actually be trained on unpaired data. So there is a lack of LDR and HDR paired data. We only have a set of LDR images and HDR images, and we need to train the model without having proper one-to-one mapping between this data. So in this case, we actually tried to modify the original cycle GAN model. So I think all of us are aware what a GAN does. So a GAN generally tries to optimize between its generation and its catching of whether the generated image is fake and or it is real. So normally there is a generator and there is a discriminator. The generator generates the image. The discriminator tries to catch whether the image is the real image or generated image. And there is a min-max game between the generator and the discriminator, which finally allows the model to perform better in its generation process. Okay. So here in cycle GAN, we have two sets of generators and two sets of discriminators. Okay. So two generators generate from one domain to another domain, and again from the new domain to the old domain. And the discriminator does the same thing as it does for a single GAN. So it tries to catch whether the generated image is real or it is fake. So in our case, what we do is that we take an LDR image X, and the first generator tries to take this image and generate the HDR version of the image. And then again, the second generator tries to take the HDR version and generates the original LDR version of the image. So it is a cycle. So from LDR, we go to HDR, and then from HDR, we again go to LDR. So our method in this particular work, our method compares with other state-of-the-art methods in various parameters. So IO is the input type and OP is the output type. So in case of LDR to HDR translation, so we have either single exposed or multi-exposed inputs. So in our case, our method is single exposed in nature. So we only need one LDR image as an input to the model, and we do not need multiple exposures as input to the model. Then output is either direct or indirect. That is, whether we generate the exposure levels and combine them to get the HDR, or we directly generate the HDR image. So in our case, it is direct. So we directly generate the HDR image. So these eyes are indirect methods where they do not directly generate the HDR image, but generates the exposure values. And we combine these exposure values later on by some off-the-shelf method to get the final HDR. So after that, the UP is the unpaired. So there is only one method in the state of the art that actually is trained on unpaired data, and another one that is GLOGAN in the third last line that is trained on self-supervised, trained on a self-supervised setup. Then HF is heuristic-based post-processing. So we have used a heuristic-based post-processing to further improve the generation process. CON is the contextual information, SEM is the semantic information, ART is the artifact awareness, and TM is tone mapping. So we take into account contextual information, semantic information. We also mitigate artifacts in the generated image. And finally, our method also performs tone mapping. So it can convert from LDR to HDR, and it can also convert from HDR to LDR. That's why we can perform both inverse tone mapping and tone mapping. So in this case, inverse tone mapping is the conversion of LDR to HDR, and tone mapping is the conversion from HDR to LDR. So yeah, this is the overall pipeline that we have, where you can see there are two generators, GY and GX, and two discriminators, that is DY and DX. So in the first image, image A, so we input LDR image X, we get HDR image Y cap. Then this HDR image Y cap is passed to the discriminator along with the ground truth HDR image, and the discriminator determines whether it is real or fake. And this process of determining the real or fakeness of the image, along with the generation process together, makes the generator loss. Okay, so now the heuristic-based post-processing is put in top of the generator, where we pass the generated image through a heuristic process to fine-tune the generated image and pass it to the generator as a conditioner for the later iteration of the training process. Similarly, in the down part, you can see there is a E. This E is nothing but a clip encoder. So we take the generated image and the input image, and we extract the embeddings from this clip encoder, concatenate it, and pass it to the generator as a conditioner along with the heuristic to better make the generator learn to generate HDR images, looking into the difference between the input LDR and the generated HDR via the clip embeddings. Similarly, in the right-hand side, you can see the same thing happens, but we take the HDR image Y as input and get the LDR image X. So there is a cycle consistency between the process. So we first give X, we get Y. Then again, we give Y, we get X. And similarly, we first give Y and we get X, the reverse of the process. And then we give X and then we get Y. So we have a cycle loss between the ground truth X and the generated X, again the ground truth Y and the generated Y. And this ensures that the generator GY and GX along with the discriminator DY and DX are consistent with the inputs and the outputs. Okay, so this is how we leverage the power of cycle GAN to make the model self-supervised in nature, and it doesn't require ground truth label paired data, which actually have a pair like X as LDR and Y as HDR. So we just need a set of LDRs and HDRs without having one-to-one pairing to train this model. And in this case, so we also propose a novel generator in the form of a unit, which also has a feedback mechanism, which actually refines the generation process. So this feedback mechanism actually works in 3 iterations, and the red color blocks after the feedback mechanism are inside this iteration, and the blue color blocks are outside this iteration. So this iteration count is 3 in our case, and we iteratively refine the generation process in the output layers using this feedback mechanism. And finally, the skip connections provide the initial features from the LDR image, pass it to the final layers of the unit. And in the right-hand side, you can see the heuristic process that we use to, generate underexposed, overexposed, and artifact aware masks, which are fed into the generators as shown in this figure to further refine the generation process. So these are the losses used, as I already discussed. So there is one heuristic-based loss where we actually extract the overexposed, underexposed, and artifact areas from the image and use these pixels to actually mitigate the number of pixels generated in this particular areas in the next iteration of the training process. So essentially, we're actually trying to mitigate the overexposure, underexposure, and the artifact areas in the generated image using this particular loss. Then we have a segmentation-based loss where essentially we try to take the input image and we run a segmentation model and we get the segmentation masks. Then we take the generated output and we run the segmentation model and we get the segmentation mask, and we find the difference between this segmentation mask of the two generations from the input and the output and try to minimize this difference between these two masks. And there is a contrastive loss which is run on the batch. So suppose we have a batch size of 4 and we have this input LDR image in the X and HDR image in the Y. So this contrastive learning, what it does is that it tries to minimize the difference between the positive pairs and maximize the difference between the negative pairs in the between these images. So essentially, when we give an input X to the model, we get the output Y. And this input X and output Y will be considered as a positive pair because Y is the output from the input X. But if for the same image, now there are 3 different other images in the batch that is not the first image. So now for these images, the input and the output, the first output Y and these 3 inputs will be negative pairs. So this will happen for all the input images and the output images. So the green color arrow marks the positive pairs and the red color arrows marks the negative pairs. And this essentially will let the model learn how to create positive pairs from an image and not the negative pairs. So this will essentially ensure semantic and contextual consistency in the generation process. So when we have an image with certain objects like, let's say, humans, cars, or seaside, mountainside, so the model will know that the model should not hallucinate the areas in this image. For example, the sea area or the mountain area should not be hallucinated with a building area or a human area. So the model will learn the contextual meaning of the image using this contrastive loss, and then will reconstruct images which are contextually and semantically consistent. Okay. And of course, the cycle loss, as I already explained. So if we give an input X, we get Y, and finally we get the X cap, that is the original input. We find a loss between this X and X cap. Similarly, we find a loss between this Y and Y cap to mitigate the difference between this X and X cap and Y and Y cap in the cycle loss. And this happens for all the iteration of the training process and ensures consistency of the generation process, the generators GX and GY using this cycle loss. Okay. So yeah, so these are some of the results that we have achieved compared to other state-of-the-art methods which are either supervised or unsupervised. So the first subtable are all supervised in nature, and the second subtable are either unsupervised or weakly supervised or semi-supervised in nature. And ours is, considering the cycle gain architecture, it can be called as a self-supervised model. Although we rely on data for training, but it is not paired data or not one-to-one map data. So we can see that in case of 3 matrices, our method is performing the best, and only in PSNRs, another supervised method is performing best compared to all the methods that we have used. Okay, we have also done some other tests on mixed data sets, unpaired data sets, and we have established the supremacy of our model compared to other unsupervised methods across these 4 matrices. And then we also tested the tone mapping part, that is the reverse part, HDR to LDR part. And we saw that our method's tone mapping part, that reverse part, is performing good in 2 matrices. And it is performing second best in case of PSNR. So there is another method called deep TMO that performs best in case of PSNR. So considering that our method has both the LDR to HDR generation process and HDR to LDR generation process, so this is pretty decent result as compared to other methods who have used more complicated or complex tone mapping algorithms or methods in their work. So this is an ablation of our generator to show why our generator is better and why using any other generator can or may not be as good as what it is right now, what our model is generating. So there is a unit from where we got inspired, and we actually modified our unit for our particular generator purpose. So that is another method that was published in 2023 WACV, which is called single HDR. So the first column is input LDR. The second column is the output of the state-of-the-art methods, single HDR, using the unit-based structure. And you can see there are lots of artifacts generated in the images. In the wall, you can see some artifacts. Also in the second and third images, if you see closely, there are some artifacts generated in the sky area. But when we modified our unit to accommodate the feedback mechanism in the final layers, and also the conditioning by the heuristic-based method as well as clip-based encoder, we found that the artifacts generated are removed, and this actually establishes the supremacy or the efficacy of our modified generator compared to existing unit-based models that are being used in this domain. Okay, so now these are some of the ablations in the different losses. I will not go into the detail because it is not that important at this point. So how our loss contributes towards the final output, visual output quality of the model. And these are the final results of our model's output compared to other state-of-the-art models. So you can see our model closely resembles the ground truth HDR compared to the other models. So there are a lot of artifacts. So in the top image, you can see lots of artifacts in the light area. So the light falling on the wall. So there are some artifacts generated in all the other state-of-the-art methods. But our method is generating smooth light and wall interaction, and also similar to the ground truth HDR. Similarly, in the lower part, you can see lower image, there are a lot of artifacts generated in the sky region where there is overexposures. So in our method, our method's output is artifact free to a great extent, and also similar to the ground truth HDR image. So yeah, so this is the third work that I wanted to discuss today, which actually uses unpaired data for training, and self-supervision is also a trait of this model. And finally, coming to the last part and the most interesting one, so the physics-based modeling in HDR generation and how we have used it in this case, and also can be used in other image translation or video translation tasks. So some of us might know that there are two types of surfaces in real world. We call those as either specular surfaces or Lambertian surfaces. Okay. Now, these specular surfaces are surfaces which are normally shiny in nature. And when light falls on these surfaces, it tends to reflect in only one direction, as shown in the right-hand side. But when light falls on Lambertian surfaces, it actually diffuses into all direction and equally reflects from all the direction or from all the point of the object. So normally rough surfaces are Lambertian or diffuse in nature, and shiny surfaces like glass, floor, or metallic objects are specular in nature. So here is an image to actually describe the concept. So here is a artifact in the floor, and the base is of stone, and the top part is shiny metallic. So the top part is actually specular, and the base part is Lambertian or diffuse. Similarly, the floor is specular in nature because it is shiny. The glasses are specular in nature because those are shiny. So in the lower part, there is a table to categorize the different surfaces, whether they are specular or Lambertian. So on the basis of whether the object is specular or Lambertian, there is either specular reflectance or Lambertian reflectance to define this. And this largely, defines the interaction of light with these surfaces. So it is important to model this particular specular and Lambertian reflectance in image generation process so that the light object interaction or shadow object interaction remains consistent with the ground truth. So here is another example where you can see the same object, if the roughness is less, how it becomes shiny in nature, and if the roughness is more, how it becomes less shiny in nature. So the left-hand side image, the left-hand side ball is more shiny because we have zero roughness. The middle one is 50% rough, so it's less shiny compared to the first one. And the last one is 0% shiny or 100% rough. And you can see the difference. So how light is actually reflected from only some particular points in the shiny surfaces and from all the points in the rough surfaces, so equally. So that actually marks the interaction between rough and shiny surfaces in a particular, object. So to this end, we have actually created a model inspired by this physics of lighting and shadow, which actually is a very recent work that we have done and under review. So we have this ground truth LDR image in the left-hand side, and in the middle there is a reconstructed image from CVPR25, a method from CVPR25 using diffusion model. And finally, our model's output in the extreme right. So you can see how the overexposed or highly lit areas are reconstructed with high clarity, and the reflections in the floor and the shiny surfaces are reconstructed in a much more realistic and visually pleasing way compared to the state-of-the-art method in the middle image. So now going into the architecture, what we have done here is that we use a VAE, so autoencoder based diffusion model. We use two encoders, one decoder, one clip-based encoding, and two different state-of-the-art models for depth perception and illumination perception. So here in this image, you can see we use this DA. DA is the depth perception model. VIT is a illumination perception model that gives us the depth map and illumination map of an input image. And the LDR ground truth is the L, the HDR ground truth is H, and the generated HDR is the H cap. So we first pass the HDR through encoder E that is trainable in nature, and we extract the latent code. We add Gaussian noise over an iteration of 1000 time steps for the same image. Then we concatenate it with a conditioning from the encoder E dash, that is the encoding of the LDR ground truth. Then we pass this concatenated information to the unit-based diffusion process that actually predicts the added noise in each training state. So in this diffusion process, the reverse diffusion process used in the unit, we also try to condition this unit using the clip embedding. That is a concatenation of the illumination information from VIT and the depth information from DA model. And these are actually pre-trained and frozen in nature. The only trainable part here is the encoder E that encodes the HDR image, the decoder D that decodes the final HDR image from the predicted noise, and the HDR diffusion process that actually reverses the forward process. The forward process, we add noise. The reverse process, we denoise the data. So the diffusion takes place in the latent space, while the feature extraction takes place in the pixel space. So the green color block is the pixel space. The purple color block is the latent space. So hence, we are using a latent diffusion in this process. So and we use two different losses. One is the diffusion loss, conventional diffusion loss, LD. LD tries to sample the HDR features from the Gaussian distribution, the Gaussian noise added to the ground truth HDR plus the conditioned LDR and the clip conditioning from DA and VIT, the illumination and depth information. And then we try to mitigate the difference between the added noise epsilon and the predicted noise epsilon theta. Epsilon theta is nothing but the HDR diffusion process that takes in the latent representation from encoder E, the added noise epsilon, timestamp T, then the encoder E dash for the LDR, L, and finally the L embed. L embed is nothing but the combination of L depth and L illumination passing through the clip. So the illumination and depth information that is been embedded through clip embedding is called as L embed in our case. So this is the LD is the diffusion process, and L met, the second loss, is a very simple loss, a novel loss that we have actually designed in our method, where actually we decompose the ground truth HDR image into material maps and the generated HDR image H cap into material maps. These material maps are nothing but the maps of this image that actually distinguish the metallic, the rough, and the albedo. The metallic and rough is inspired from the description that I gave in the introduction part here. So all the metallic parts in the image and the rough parts of the image are segmented out. And we also use a third map, that is the albedo map, that actually defines the base color of the objects in the scene. So essentially, when light interacts with an object in a scene, then the original color of that particular object tends to change. For example, in this image, lower part, you can see that the photographic texture is the image where where the light object interaction is shown. So when light falls, there are some changes in the intensity levels of the object's pixels, which actually tend to change the base color of the objects. The albedo map is the map in the right-hand side that actually gives you the color when we remove the light interaction from the object. So it is important that we also take into account the albedo correction part in the generation process. Otherwise, the generated HDR image may generate some arbitrary color of some of the objects in the scene. So now these material maps are nothing but the decomposition of this image into three different maps: the albedo map for color information, the roughness map, and the metallic map for specular objects and Lambertian objects, as I discussed in the previous slide. Now we mitigate the difference between these material maps generated from the HDR image ground truth and the generated HDR image using a state-of-the-art. So we generate these material maps using a state-of-the-art decomposition method. And then we find an L1 loss between these maps that is shown in the equation in the lower part, L map. And finally, we try to mitigate the difference between the generated material maps and the ground truth material maps. And this loss is then backpropagated through the diffusion process to make the diffusion process more inclined towards physics-based light object and light shadow interaction. Okay, so we have seen that our method is generating better quality results, as well as quantitatively it is better for 3 matrices only to be second best in PSNR. So here we use the VDP3 metric, not the VDP2, that is more recent HDR comparison metric compared to the older one, that is VDP2. So we see that for intra dataset, the first table, our method is best for one dataset and best for another dataset, only second best for PSNR. The second table gives the results for a cross dataset evaluation also, where we tested the models in a dataset that is not seen during training. So completely unseen dataset. And we see similar trends in this dataset as well. And we see that our method performs the best. And ghost-free and LEDIF. LEDIF is another diffusion-based model, which performs second best in terms of PSNR, SSIM, and LPIPS and VDP3. So these are some of the visual results where you can see our methods generation is more physically plausible compared to other method in terms of light object interaction or light shadow interaction. If you see closely, you can see the areas where there are lights, shadows, and light falling on shiny surfaces or diffuse or Lambertian surfaces, how the light is behaving, how accurately the light parts are reconstructed in our images compared to other state-of-the-art images. So yeah, this is pretty much the thing that I wanted to show. With this, I think I conclude my talk on this topic and open for questions, if any. Thank you so much.
Thank you, sir. So the questions will be in the chat box. The participants can write their questions.
Yeah, sure. Yeah, I can see some
Sir, those questions
questions.
are from previous sessions.
Oh, okay, okay. These are some previous. Okay.
We will wait for 1-2 minutes if someone like this. Sir, I think there is no questions. No one is asking
Yeah.
anything.
Okay. So
Okay.
I think, yeah, if anyone has any question, then they can directly reach
Mail
out to
you.
me later on via email or something. Professor Deepak can share my details and they
Yeah.
can reach out to me, no issues.
So I sincerely thank Mr. Rishabh for joining us and sharing his valuable insights. I would like to extend my gratitude to all the participants for being a part of today's session. With that, we formally conclude the session. Thank you, sir. Thank you, participants. Thank you, sir. You can give.
Thank you so much for having me. Thanks.